Today we continue our discussion of combinational logic with a focus on logic conversions. That's conversion between equations, truth tables, and circuits. We're going to explore something called the don't care operator, which we'll identify as an X, and we'll see that that will help us simplify our circuits. With regards to combinational logic, we have Boolean equations. Some of those are simplified. Some are definitely not simplified. We also have things like the sum of minterms equations. There are circuits with many different styles. For example, you might find the array style, or maybe the inversion bubble style. And once again, some of these may be simplified, and some of them may not be simplified. There's also the truth table. And we'll note that there can be only one truth table. While there may be many circuits or equations that point to a particular truth table, there can only be one truth table for any given equation or circuit. If we were to put that into a picture form, we might encounter circuits that are built with, say, only NAND gates, or circuits that are built with a combination of many different types of gates. You might encounter an array style. Each of these circuits in turn can point to a specific truth table. We could make a circuit out of NAND gates. We could make a circuit out of a combination of various gates. We could make a circuit in array style. Either way, you can envision a situation where each of these circuits would point to the same truth table. We call this the canonical form. There can be only one truth table for each circuit. Another way of saying that is there can be only one compact sum of minterms equation. I suppose if you wanted to get fussy, you could argue that the statement about the truth tables and the statement about the compact sum of minterms are one and the same. Because for any given circuit, right, if you build a circuit with all NAND gates, when that circuit is done, it will have a truth table. That truth table can be described as a compact sum of minterms. As we implied earlier, we have equations, we have circuits, and we have a truth table. One of our objectives is to be able to transition back and forth between these various forms. Given a circuit, a logic gate circuit, we should be able to find a truth table. Given a truth table, we should be able to find an equation. Given any one of these three, we should be able to find the other two. As an example, I'm going to present three different representations. The first one, F is equal to D naught, C naught, or CA, or D naught A. Our next circuit is G. Given inputs D, C, and A, we have an output G. This is the first circuit we're going to consider. This is the second circuit we're going to consider. And now here is the third circuit. And we'll let that be expressed as the function h with inputs D, C, B, and A is equal to the compact sum of minterms with terms 0, 1, 2, 3, 5, 7, 13, and 15. What we want to do now is we want to look at each of these three circuits and determine if they are the same. When we use the word same, we're talking about that truth table, the canonical form. This circuit can only have one truth table. This circuit can only have one truth table. This circuit actually describes a truth table, but there can be only one. And again, what we want to know is, are these the same circuit? Is function f the same as function g, the same as function h? Let's start by looking at function f. I'm going to write it here for convenience. To get us started, let's make an assumption. Let's assume that this particular function f has 4 inputs. You'll notice that this input b does not appear in any of the terms. It's almost as if we don't care about b. We could represent the don't care with a x. Rewriting f using that don't care idea, f is equal to d naught, c naught, ANDed with b, which we don't care what b is, ANDed with a. We don't care what a is. Or we don't care what d is, but we're interested in c, not interested in b, interested in a. Or d naught, don't care about c, don't care about b, care about a. This is still the same equation, it's just that we've added the don't care for the various terms that we don't care about. Now, watch this. If we take this first term, d naught, c naught, the circuit would still operate exactly the same if this was b naught, a naught. It would operate the same if these were the inputs. Or we would identify this as minterm 0, minterm 1, minterm 2, and minterm 3. In all 4 of those cases, this term right here would be active. We can expand that next term like this. Let this be c and a. We're going to write it 4 times. This first x could be d naught, and this could be b naught. B, b naught, b. We'll let this be d naught, d, and d. As far as minterms are concerned, this is minterm 5. This is 7. This one is 8 plus 4 plus 1, which I believe is 13. And this is 8 plus 4 plus 2 plus 1, which is minterm 15. Now we can look at this term. So that is combinations where we have d naught and a, not caring about c and not caring about b. C and b can take on 4 unique values. So c naught, b naught, all the way to cb. This is minterm 1, minterm 3, 5, and 15. Correction, not 15, 7. You'll notice there's some duplication in here. Minterm 1 appears twice, 3 appears twice, 5, and 7. All of those appear twice. Our function f, with inputs d, c, b, and a, can be written as the compact sum of minterms with minterms 0, 1, 2, 3, 5, 7, 13, and 15. Looking back, that is indeed the same as function h. Let's go ahead and give this a name. Let's call it term expansion. With this technique, we took a term that was decidedly not a min term, and we expanded it. For those missing terms, we put in the don't cares, and when we expanded it all the way, we were left with the min terms. We then collected all the min terms together and came out with this equation right here. Now that that's done, let's go back and look at this gate level circuit. We've done this several times in the past. We've taken a gate level representation and we've converted it into a truth table. For this circuit, this first intermediate wire is D0, C0, and the second intermediate wire here is CA. If you put those two together on the output, that would be G is equal to D0, C0, or CA. Building that truth table, we would have D, C, B, and A as inputs. D0, C0 is intermediate wire. CA is an intermediate wire. And finally, output G. For the intermediate wire D0, C0, we're looking for D0 and C0. That looks like that's the only place that occurs. So this would be 1, 1, 1, 1. It would be 0 for all others. For the intermediate wire C ANDed with A, that would be here and here, ANDed with A. So 1, 2, 3, 4. So that occurs in 4 different spots. 0, 0, 0, 0, 0, 1, 0, 1. Now we OR these two together to form G. I believe that's what this says. Yes, that is an OR gate. So we OR these together, and we end up with 1, 1, 1, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 1. Let's make another column here, and we'll call that min terms. So that's min term 0, 1, 2, 3. Nothing on 4. Min term 5. Nothing on 6. There is 7. 8, 9, 10, 11, 12. And we have min term 13 and min term 15. With that done, we can now compare this circuit to this circuit. So we're comparing G to H. It looks like we've been successful. Here's min terms 0, 1, 2, 3. So that's these 3, 5, 7, and 13, and 15. So circuit H is identical to circuit G. In fact, at this point we could stop and we could declare that F, G, and H are all the same. We worked on circuit F here, and we declared that it had these as min terms. We worked on the circuit G, and we declared that these were the min terms. And of course, circuit H had the min terms already listed. So it looks like we're in good shape. Circuits 1, 2, and 3 are indeed identical. But let's keep going. Let's try this a couple of different ways and see if we come up with the same answers again. For example, let's take this G function right here and expand it to see if we can find the min terms directly using the Boolean algebra. We'll rewrite it here for convenience. As we did before, let's expand that. So we'll assume it has 4 inputs. D0, C0, don't care about B, don't care about A, or don't care about D, care about C, don't care about B, A. We can now expand that as we did before. giving us minterms 0, 1, 2, and 3. The second term expanded, gives us minterms 5, 7, 8 plus 4 plus 1 is minterm 13, and finally minterm 15. Converting that to our compact sum of minterms, we end up with the same thing we had before. Minterms 0 through 3, 5, 7, 13, and 15. Once again, we've shown that circuit G is equivalent to circuit H. Let's try this again, except this time, let's start at the minterms and see if we can use Boolean algebra to find a simplified circuit. We'll start with function H. We said that was the compact sum of minterms, like so. This can be rewritten as a sum of minterms. In fact, let's write that down. So sum of minterms. And just to be complete, we're going to call this the compact sum of minterms. All right, so the sum of minterms, H, is equal to D naught, C naught, B naught, A naught. That is this minterm right here, minterm 0. Or minterm 1, or minterm 2, or minterm 3, or minterm 5, minterm 7, minterm 13, and finally minterm 15. Since we've already worked this problem a couple different times, I think you already know where we're headed. We can simplify this equation by factoring out D naught, C naught. So that's this term, this term. Next, we're going to look at these minterms, and we're going to factor out CA. Continuing on with the simplification. Once again, and our final step tells us that function H may be simplified to D naught, C naught, or CA. That does look familiar. If we scroll up to the top, that was the output of our function G gate level representation. It's also very close to function F, except it looks like function F had this piece right here, which was redundant. To see what we mean by the word redundant, let's take a look at that thing called a Kmap. Again, we're getting ahead of ourselves, and I'm not going to explain why, but I'm simply going to make the Kmap and then show you the redundancy. The Kmap has inputs D, C, B, and A, with inputs D and C running on this side, inputs BA on this side. The output for each condition is read from the grid. For example, if D, C, B, A are all true, that would correspond with minterm 15, which means there would be a 1 in this cell. If the input was D naught, C naught, B naught, A naught, that would correspond with min-term 0, which means there would be a 1 in this cell. Now, as far as the rest of the min-terms are concerned, it goes 0, 1, 2, 3, because you can see that's number 3, and that's the number 2, 4, 5, 6, 7, where it's C is 1, B is 1, A is 1, so that's where our 7 comes from. 8, 9, 10, 11, 12, 13, 14, and finally 15. So now if you look at your notes, you recall we had function h having min-terms 0, 1, 2, and 3. So all those min-terms were true. Then we had min-terms 5, 7, 13, and 15. As far as the Karnaugh map is concerned, once you have the min-terms identified, you can look for a simplified circuit by looking for numbers or cells that are adjacent to each other. For example, these could all be circled. We would interpret that as D0, C0. Let's go ahead and write that off to the side here. So that's D0, C0. We would also identify these as being adjacent. That block is known as, let's see, here's a condition, so C must be true, and it looks like A must be true. So this block is CA. This is good because that's the same results we achieved when we simplified the circuit. So H is equal to D0, C0, or CA. This is very good, but remember the reason we came down and looked at that Kmap to begin with. We were talking about this term here and how it somehow seemed as if it was redundant. So that's D0, A. Let's go back down to the Karnaugh map and let's look for condition D0, A. So D0 would be here and here. So it's these two rows. Now we're looking for a condition where A is true. So that's here and here. So D0 and A means we're circling these four right here. And if you go back and you look at your notes, you'll see that D0 A expanded to min-terms 1, 3, 5, and 7. We would call that redundant cover. And we would call these two prime implicants. Anywho, this Kmap can be used to find an optimal solution. I think you see how that works. We make this Kmap, we populate it with the various min-terms, then we make a couple of circles, and we can make a statement that says this is the optimal circuit. This also allows us to see that this term, this D0, A0 term, can be part of the circuit, but it's not absolutely necessary because every min-term is covered by D0, C0, or CA. There will certainly be more to follow as we continue on with these discussions.